and here. This would be a point which has 0 time-like size in the left-moving coordinate. So that means that it has, I don't know if I got left-moving and right-moving correct, but the point is that it has 0 size in this L coordinate. So that means that this guy here is going to be 0. But the other coordinate is non-zero because it's above the bottom of this diagram. So this guy would look like a light-like interval. It's a collapsed version of a causal diamond where one of the light-like directions is 0. And of course there's a counterpart to it which has 0 size here and a non-zero size there, and this one will be a collapsed light-like interval of this type. And if I want to talk about points which live both at the bottom, both in the left moving and in the right moving consider, that means that I have collapsed both sizes, and that would be some particular point. So notice that the CFT itself is part of this kinematic space, but it's the part where I put all the time-like directions to 0. Good. Now, oh, and let's do one more example because it's sort of important. So if I'm in a, this one will be easier to draw if I, instead of drawing things on the plane, I actually draw things on the entire cylinder. So here is my CFT cylinder. The white point, which I have over here, which is this causal diamond, was embedded like this as part of my CFT, yes? But then there's always the complementary causal diamond, which is the one which starts over here, and it goes all the way around, and all the way around, and reconnects there. Do you see what I mean? And then it connects on the other side. So where is that guy going to be? Well, this is the one that has to understand where it is, it's best to start from the case where this causal diamond was actually just a point. So if this is a point, then the complementary causal diamond is the boundary of the entire Poincaré patch. It's the whole causal diamond that wraps back on itself. So the counterpart of that type to that blue point over here is going to be something which in the light-like direction has a width which equals 2 pi, so that it can go all the way around. Which means that rather than being at the bottom of this thing, this is where L is equal to 0. In fact, I have to have L equals 2 pi and L bar also equal to 2 pi so that I can go all the way around, so that my causal diamond can have the so that my causal diamond has enough size to wrap all the way around the cylinder. So the counterpart of this guy is going to be over here. This is the maximal causal diamond. And you can see that.
Sorry,
yep.
Can you choose some sort of like a convention so that the past of the cylinder corresponds to your CFT and the future corresponds to this?
Oh yes, it's true that the way when I wrote the CFT here, then there was a time-like direction here, and I had to choose which way the time-like direction goes. So that I had 2 choices. Either the time-like going to the future could mean getting my points closer to each other, so I zoom on a point, or farther apart from each other, so they zoom to one another as well, but leaving the entire causal diamond behind. So that's just a choice I made, and let's assume that the bottom is the CFT, where is points in the CFT, whereas the top is like boundaries of Poincaré patches. Okay. Okay. So yeah, so that's what this guy is. And notice that I drew it on the opposite side of the blue thing. Why did I draw it on the opposite side? Because the midpoint is here, but the midpoint of the opposite is actually going to be on the other side of the cylinder. Yes? So that's why in the space-like direction, I didn't want to draw it here, but I wanted to draw it on the other side of the circle. So the relation between the blue one and the yellow one, the relation between one causal diamond and the complementary causal diamond, is that the same amount that I was in the time that I was above the past boundary, now I am below the future boundary. And if I go from one side on the spatial circle here, I will go to the other side of the spatial circle. So there's a natural, what we would call involution on this de Sitter, which takes a given point and maps it to the one which is spatially on the other side, and time-like, it's the same distance from the future as this one was from the past. So that's what I did for this guy. But for the white guy, I could do the same thing, and it will end up going, let me take another color. So if the white one was here, then I would draw a similar circle, sort of on the other, the same amount below the top as this one is above the bottom, and rather than drawing on this side, I would draw it on the other side. Okay. So that's my complementary diamond. Is everyone okay with that? Okay, so this is the object that we will be studying. Yes?
Is it possible to construct the kinematic space but for thermal AdS?
Well, so
geodesics and
good. So that's a good question. So it depends what we mean by a kinematic space, and I have written papers on it. So the answer is yes, on some level. But the way that I have presented this material, it doesn't jive with that. And the reason why is that I started from the quotient of the full symmetry group, of this full conformal group. But if I'm in thermal AdS, then the temperature breaks conformal symmetry already. So my kinematic space has no chance of being this object because it's not. So if I have a kinematic space, it won't be this because I have broken this part of the symmetry, so it won't be that quotient. So I have to define better what I mean by kinematic space in that context. Now, I may still talk about the space of geodesics.
you will also have some sort of constraint as you move, as you move apart the points. The geodesics will explore the kind of bulk. Then you have a black hole, right? So.
I mean, all of these. So yes, I agree with all that. Anyway, so I have. So the point is that we can start. We can define what we mean by kinematic space in different ways. The way I've defined it as a quotient of conformal group would not be applicable in that context. But I can take as my starting point the definition that I want the space of geodesics, and see if I can define some metrics still, even though conformal symmetry is not going to fix it in this using this argument, but maybe some other argument will fix it. And I have myself and other people have written papers that explain how to do it and what you can get out of it. It's also true that it depends on what it's useful for. So many of the things that I will say to you today and tomorrow, some of them will survive that kind of application, some of them will not. Yeah, so the answer is it depends on what the goal is.
I have another question.
Yeah.
Since you are using only the symmetries of the CFT, then this would apply also to asymptotically AdS spaces, no?
Absolutely, yes. Okay, so hang on. Yes and no. So I thought you were going to say something else, which is it's going to apply to all CFTs regardless of whether they have an AdS dual. And if you say that, my answer is automatically yes, definitely. So I've been talking about geodesics because that's my primary motivation. But in fact, you can talk about everything that I have said so far applies to any CFT at all. In fact, that's part of the point of doing this whole exercise, is to show that many of the, and I will talk about this tomorrow, many of the things that people have first derived as applying to AdS CFT in particular turn out to be kinematic statements that apply to any CFT in general. So, which in some cases can be very surprising. For example, people have derived linearized Einstein's equations from properties of entanglement entropy using Ryuta-Kayanagi. So notice that there are a lot of inputs here which are, and the whole point is, the whole statement makes sense only in the context of holography. Because I need to have Ryuta-Kayanagi, it only applies in holography. And furthermore, I'm supposed to be deriving Einstein's equations in the bulk. Well, what bulk if there is no AdS dual, yes? So in Einstein's equations, gravity, it turns out that an equation of the same type can be derived for any CFT. So in fact, it had nothing to do with AdS CFT. It was just a kinematical fact about conformal symmetry. And this will come out very naturally from this formalism. So if the question were, and that wasn't your question, can you do it for any CFT? The answer would be yes. If you ask me about doing this for other asymptotically AdS geometries in the context of AdS CFT, that means that it's kind of like the other question that was asked over there, which means that suppose that I'm in some non-trivial background. Well, what created that non-trivial background, like I said yesterday, in AdS CFT, we say that this is some heavy operator which created that background. There will be some heavy operator which sort of annihilates that background, and I'm computing correlation functions of other operators in that thing. So the statement is, can I take the application of these two heavy operators, and can I sort of incorporate it into an argument of this type to define a new object, an object that now knows about the application of this heavy operator? And the answer to that question is that in some cases we know how to do it, but in general we don't. In AdS free CFT2, we more or less know in full generality how to do it, and that's because heavy operators are that's because AdS free, gravity in AdS free is topological, and so that means that all I can do, every solution is going to be locally AdS free. So all I can change is just how I put the cutoff on my AdS space. So all that these operators are doing is essentially just changing the cutoff. So and we know how to deal with that. But in higher dimensions we don't. So yeah, and I depending on time, I will say more or less about this tomorrow.
I'm tempted to ask another question.
Go, yeah.
This Grassmannian structure has to do with the Grassmannian that comes in the calculation of the amplitudes? Something to do?
Oh yeah, that's an excellent question. So the short answer is no, but in fact, if I compute 4-point functions, then the answer is yes. In the Grassmannian in amplitudes is the space in which it lives is the space of kinematical data. So if I compute a 7-point function, then it will be a Grassmannian in a dimension which is like 7 times the dimension of the space-time. But that's sort of like this because this kinematic space here, it has 2D dimensions because the space of pairs of points. The Grassmannians that show up there are Grassmannians in the spaces of triples of points, quadruples of points, and then for a 7-point particle, amplitude will be in 7 tuples of points. So it's like a baby version of that. It turns out that 4-point functions can still be computed usefully in thinking about this language, but going higher, not really. But another thing that changes when you go to higher dimensions, that remember, I said that 2 points are completely homogeneous, 3 points are still completely homogeneous, but 4 are not. And 5 and 6 are even more not homogeneous, yes? So those other sort of kinematic spaces that you would have will not have these quotient forms, but instead they will have honest-to-God coordinates, which are not fixed by symmetries, and those coordinates we would call cross ratios in conformal symmetry, in conformal field theory. So these Grassmannians live in the space of cross ratios. So in that sense, they're kind of like what we're talking about, but a higher dimensional version of that.
And regarding the previous question, there you were talking about still living in a CFT, but going to a non-vacuum state, which is what was created by this.
Yeah, over here, yes. Yes.
Just to take you one step further in that direction. What about if we go to a non-CFT, to a CFT that has a UV fixed point? So now that I deformed the theory, I guess correctly, you assume all of this would work there, except you're not to do it.
Yeah. So okay. So let's see. Yeah. If you deform. Okay. So. Yeah, that's a subject for a bigger conversation. So I'm not going to answer that question right now. Yeah. Because there is no, so any such deformation is going to break conformal symmetry. So then almost everything that I have said will break down. But you might be able to redo it just by working hard. And actually, let me give one more piece of answer to this question. I think maybe in 2 or 3 days, James Sully and Andreas Karch and somebody will have a paper about kinematic space for defect CFTs. This is sort of the easiest way to break conformal symmetry by introducing an explicit defect. It's even easier than a thermal state for various reasons. So that's a place to look for. I mean, it's not out yet, but it will be out very soon on how to go further.
That will be with a defect that preserves a certain amount of conformal symmetry?
That's correct, yes. So this is for, so really what this is like CFTs coupled to higher dimensional CFTs, and then you have some interesting interplay between, between various ingredients of what I will say next. Yeah. Okay, and I want to say one more thing, which is on this geometric stuff here, which is that if I form this 4-dimensional space here, but it's interesting to take a diagonal subspace of it, which is L equals L bar and theta equals theta bar. So what does that do? That means that this size and that size is the same, and this midpoint and that midpoint are, I have to be a little more careful with what I mean by theta. But the point is that this is, I cheated a little bit here in going from the z coordinates to the theta coordinates, so pardon the cheating. But the point is that if you do this restriction, then the object that appears is obviously just a single de Sitter geometry, and that single de Sitter geometry corresponds to those pairs of points which live on an equal time slice of the CFT. So the diagonal de Sitter corresponds to geodesics which live on an equal time slice of the CFT, and what next? And in that case, there is a very nice way of understanding what the time direction means, which is even more fun and more geometric than what we said over there. So we have a space-like direction and a time-like direction in this diagonal de Sitter. Oh, by the way, rather than drawing a cylinder and then projecting everything onto an equal time slice, let me just take this and draw the circle, and time is now going to go out of the board. So that will make all the drawings easier. Is everyone okay with that? I just took this equal time, making this restriction, put us on a restricted all our geodesics to have endpoints at an equal time. Now that everything will happen at equal time, I might as well just draw the time-like slice. That's what I'm saying. So now, if I take one of these points, this corresponds to a single geodesic, which is like this. Now if I choose another point, then I have various options. One option is like this, where my other geodesic is the interval that it subtends is properly contained inside the other interval. This corresponds to, this has the interpretation of the corresponding point in kinematic space to live directly below this, not necessarily directly below this, but the point is that it lives in the past of this point. I could have also put it in the future of this point, and that would correspond to drawing something that itself properly subtends my interval. A completely different option is to have something which is space-like separated from my white point, or from my white geodesic. What is that? This corresponds to something which is not contained inside the interval. So that's something which will partly contained and be partly contained and partly not contained in that interval. But that means that they will intersect, yes? And so points which are space-like separated from one another in this language correspond to points which correspond to geodesics that intersect. And you can say, what about the borderline case? Suppose that I take this pink point and I'm going to deform it closer to the yellow point so that at some point it becomes null separated, yes? This would be null separation. Well, that means that I have to take one of the endpoints of this geodesic and move it over so that it's borderline from a situation where it's contained, but borderline away from it being not contained. When is that going to happen? When they have a common endpoint, yes? So that means that the light-like directions over here are the endpoint directions of the geodesic. Of course, we already knew that, because this is what we said on this part of the board, that light-like directions are really just the endpoint directions of my geodesic. But here we sort of see it more clearly, that deforming one geodesic will either change the property of either being contained or not being contained inside the interval that a given geodesic subtends. Are there any questions about this? Oh, okay. Did I manage to explain it, or did I just make it more confusing? All right, good. And but the thing about intersections is special to this diagonal de Sitter, where we're on an equal time slice of the geometry. If I'm away from this thing, so if I'm in a fully four-dimensional picture, which is the picture over here, then I may have one geodesic which does this, and another geodesic which does that. So these things are not going to be intersecting in general, but there's still a topological property of the causal diamonds that they define, either being contained in one another or intersecting in some way. And so you can attempt to make similar statements, but you have to be more careful about what you mean. The geodesics don't intersect when they're off from a time slice, and there's a finer thing to be said about the topological relations between pairs of points. And those finer things are inscribed in the causal relationship between those two pairs of points in the left and in the right de Sitter. Things can be space-like separated here and time-like separated there, or the other way around. And that corresponds to the relevant causal diamonds only containing one another in the one light-like direction, but not in the other direction, which is what I drew for you over here. Any questions? Okay. So I want to make some further statements in this diagonal de Sitter. And in fact, this is the stuff that has really given impetus to this research program. So suppose that I wanted to compute the and again, because in the diagonal de Sitter, I'm on an equal time slice of AdS, so I'm just going to draw an equal time slice like this. Let me draw a curve like this, and I want to give you a problem, which is compute the length of that curve. What is it? So it turns out that okay, so my kinematic space, let me draw it over here. I want to consider the set of all geodesics which intersect my curve. That means these geodesics and those geodesics, all of that. So the set of all geodesics that intersect that curve. Again, if we're off from a time-like direction, it wouldn't be so easy to define, but having the luxury of living on an equal time slice means that it's easy to define what I mean. So these geodesics are going to form some band in kinematic space. How do I know that they will form a band? Well, because geodesics that live over here are the ones that are very small, and these are the ones that are not going to reach to the boundary. Or the ones that live over here are actually the same geodesics correspond with the opposite orientation. They correspond to wrapping almost all the way around the CFT. Again, they will not reach the curve. So the ones that do reach the curve are going to define some band for me over here. And it turns out that if I take d volume in kinematic space of this band, d volume kinematic space, over this band of geodesics, which let me just write here as intersecting geodesics, then this equality holds. So one way of computing the length of any curve is just taking the volume of kinematic space that lives there. What do I mean by the volume of kinematic space? Well, I have this de Sitter geometry, and this de Sitter geometry has some volume form, and so we derived the metric, so we know exactly what this means. In fact, we can write this metric kind of explicitly because we know that our de Sitter space has exactly this form. The two de Sitters was this plus that, but I made this identification, okay? So now I just have a single L and a single theta. And what this is an integral d theta dl over sine squared L. That's just what I read off from here. Okay. And let me just write down again my metric, which is minus d L squared plus d theta squared over sine squared L. So that's just a fact, and that's a very nice fact, because let me just make some emotive comments about it because I'm excited. So here is a curve, which is some object. Now, so far, we knew how to interpret only one type of curve, which was a geodesic itself. So if I had a geodesic, we had two interpretations for it. One was in terms of entanglement. Remember, we're in d equals 2 right now. So our minimal surfaces that Ryuta Kainagi told me about are, again, just geodesics, yes? So this thing computes for me the entanglement entropy of this interval. Okay, so far so good. Or also the exponential of its length is going to compute for me the 2-point function of operators that live over there. Yes, these were the two things I knew about it. Somehow, but that's only about geodesics. So now I give you some arbitrary curve, and it turns out that AdS knows about properties of this arbitrary curve through a formula that only cares about geodesics, which means that we can start telling stories about curves of this type. So one story I can tell, I'm not going to write it down, but let me just say it, is that the length of a closed curve, it counts geodesics, that's what we would say given this equation, which means that it counts all 2-point functions which are sort of infrared enough. What do I mean by infrared enough? This is a geodesic, which is this geodesic computes a 2-point function, which is fairly UV. This is a geodesic like this, computes also some 2-point function, which is fairly infrared because the points are sufficiently far apart from each other. So every curve computes for me how many 2-point functions are sufficiently infrared. And what I mean by sufficiently infrared is given by the shape of the curve. So that's one type of story that I can try to tell. And by the way, for people for whom it wasn't obvious that what I meant by UV and infrared, the near boundary region in AdS corresponds to the ultraviolet of the theory, whereas the deep region in the bulk corresponds to the infrared of the CFT. And one way to see it is that the geodesics that stay here are the geodesics that are fixed, that compute short distance correlators. That's in ultraviolet. The geodesics that do that compute very distant correlators, and therefore they are above the infrared. Or another way to say it is that the radial direction corresponds to dilatations, which means changes of scale. So it's going to map me from the UV to the IR if I go deeper. But anyway, so this curve is somehow about, it's a collective description of many. It's not even a description, it doesn't even give me the answer to any question. It just counts how many questions involve the infrared in their answers, if you see what I mean. That's counting these geodesics. Okay, now another thing that you can say is that, okay, so that's about correlators, but we also have an interpretation of this curve in terms of entanglement entropies. And entanglement entropies were also in themselves supposed to incorporate or summarize how much correlation there is between the interior of this and the exterior of that region. That's a little different from what we meant before, because the correlations like that are the ones that I would care about if I had an operator, or one such correlation would be measured by a correlator which has one operator inserted here and one operator inserted there. But notice that this is precisely what we want, because the boundary of this region over which I'm integrating corresponds to what? It corresponds to the boundary of my region of integration corresponds to those geodesics which are just tangent to the curve. They are borderline between intersecting and not intersecting. The entanglement entropy that this length computes quantifies correlations between this part of the CFT and the rest of that CFT. So correlators that I will have, which probe this, are the correlators that have one endpoint over here and the other endpoint over there. Things of that type will generically intersect my curve, but not all of them will, okay? Some of them will not intersect the curve. So somehow we have to do a little more gymnastics to understand how exactly this formula relates to entanglement entropies. We have the right ingredients, but we don't have the right answer yet. So let me give you a way of interpreting this formula in terms of entanglement entropies. And the way we do it I really just have to write down what the entanglement entropy of an interval is. So this is given by, there's a prefactor, which is C over 3. We talked about it a little bit yesterday. It's not really important for us. Times the logarithm of the one endpoint minus the other endpoint. By the way, when I'm in a two-dimensional settings, when I'm on a static slice of AdS, I will use coordinates, which I will call U and V, where V is one endpoint and the other one is the other end, and U is the other endpoint of my geodesic. I'm sorry for multiplying coordinates, but I just learned how to think about it this way, and to avoid mistakes, I have to stick to it. So V and U are my two coordinates on this space, and they are light-like coordinates. Okay. And what I have over here is the logarithm of V minus U, which just computes for me the size of the. This is just the size of the interval. In the language of L and theta, this is C over 3 times log of 2L. Do you agree with that? There's also some stupid cutoff, but the cutoff will drop out from everything I say. Okay. So the statement that I want to make here is that if I take the second derivative of the entanglement entropy as a function of L, what will I get? C over 3 will come in front, and what I will have here is just, correct me if I'm wrong, 1 over L squared. Yes? Good. This was the result for the, I forgot this. This is the result for being on the plane. These coordinates are actually on the circle. Let me redo the same thing when I'm on the circle. Sorry about that. So in that case, I will have sine of 2L. Actually, the sine of L divided by mu. So when I take this is the formula that's on a circle and not on a plane. So when I take this quantity, what I will get is 1 over sine squared L. This 1 over sine squared turns out to be exactly the 1 over sine squared that sits over here. D theta dl in these u and v coordinates, which I introduced here, will just end up being du times dv. And so an equivalent way of writing the whole equation would be to say that this is an integral of dv du times the quantity which is, and I should say what this one is. This one is d second nth dv du. So this thing has an equivalent rewriting, which is this one, where again the integral is taken over intersecting geodesics. Now we have a very nice connection with entanglement entropies. So it turns out that the point of this 1 over sine squared, which was fixed by conformal symmetry actually in the previous argument, the point of this 1 over sine squared was that what we're actually computing is this combination or this property of the entanglement entropy. But what is this quantity or this object constructed out of the entanglement entropy? This is if I have some u and some v, okay, this is the entanglement entropy of it. I just drew a geodesic for you. What this quantity computes for me is the antisymmetric combination of lengths of geodesics, where I send u to u minus du and v to v plus dv. Then d second s entanglement du dv is actually approximately equal to s of uv plus, s of u plus dv plus s of u minus du, comma, v minus s of uv and minus u minus du, v minus dv. I just took a discrete approximation to the second derivative. So if we were to draw what these terms look like, I'm going to draw the positive terms in red, that's this term and this term, minus this term, which I already had over here, and that term. Yes? So the quantity that we're actually integrating when we do the integral is those geodesics, which is the length, it's the antisymmetric combination of geodesics, where we take that geodesic plus that one minus the smaller one minus the bigger one. Okay? Notice that we already know what this quantity is. Have you seen this picture before? Yes. So yesterday I drew exactly the same picture, actually 24 hours ago exactly, I drew the same picture, because I went over time as well, where this I called A and B and C, and this quantity was SAB plus SBC minus SB minus SABC. And I said that this thing was necessarily greater than or equal to 0 by something called the strong subadditivity of entanglement entropy. The strong subadditivity of entanglement entropy, the left-hand side of it, also is called the mutual information of AC given B. And that counts those, remember, it's a combination of entanglement entropies. If entanglement entropy quantifies the correlations between a system and its complement, then this object, which we have over here, counts the extra correlations between A and C, which are not mediated by B. So that means that in the context of our tangent geodesic, I'm counting correlations which live over here and over here, but don't pass through the middle. But they will be mediated by precisely the types of geodesics that actually intersect my curve, which is the reason why this had to be the right answer. Do you agree with, do you see why I said this? And another remark I wanted to make is that notice that this guy here is actually a measure on the space of geodesics. And you could say, oh, if you're constructing out of a CFT and out of entanglement entropies a measure on the space of geodesics, are you sure that your measure is never going to be negative? It would be a little embarrassing to say, oh, I'm going to compute my length by counting how many geodesics intersected, except some of them have to go with negative weight, so they actually anti-intersect. That would be strange. But the answer is that it never happens because strong subadditivity guarantees it. So that's a pretty nice and elegant way of how the theory resolves its own problems. Good. Any other questions? Or any questions? So in fact, what I want to say is that, so here I made the statement about the measure on the space of geodesics. But in fact, and the statements I made were given just by, or were motivated by conformal symmetry. I mean, this board is all from conformal symmetry. What I erased was from conformal symmetry. And here I was using the form of the entanglement entropy. But this one is also, we also use conformal symmetry to derive it. So you might say this is just going to work for pure ideas and for nothing else, because only conformal symmetry was needed to derive it. Now, in going to this step, I actually replaced an object which I knew explicitly with something which is more of a black box, which is entanglement entropy. So if you hand me a different state, this will actually take different values. So this equation still turns out to be true.
When the second derivative of the entanglement entropy is 0, you have the point?
Yes. When you have, so there is a subtlety here, actually, but roughly speaking, yes. So you can say that a point, oh, and can I just tell you how to easily see it? Because that's nice. So here is a small curve. I will compute the length of this curve by taking all geodesics that intersect it. But there are not that many geodesics because we have to be on a very narrow way. So the band over which I'm integrating is like this. So as I go here, as I actually zoom in on a point, all I will have is just the geodesics that actually pass through the point. This will correspond to an infinitely narrow slip of this kinematic space, so it will have 0 volume. But going to your question, you said, does that mean that that the second derivative is going to vanish, but the second derivative won't vanish because I have a zero measure region over which I'm doing the integral. But something else will vanish, which is or maybe it's not worth talking about. So I was going to go on a detour, which would take like 5 minutes, but maybe it's not worth it. Let's talk later. So anyway, that's how points are recovered. They're just lines for this thing. Yeah, there's a caveat. Not every line is a point, but every point is a line. I should also say that. Okay, but going back to what I was saying before. So up to this point, everything was just fixed by conformal symmetry. Here I introduced for you an object which was actually not given by conformal symmetry, because this entanglement entropy, if we plug in values which are not for the vacuum, this formula will also work. So, but I only did it at the level of the measure in this integral. In fact, the kinematic space metric from which this measure comes from is still unaffected. So I will still have a metric which takes this form on my equal time slice kinematic space. And moreover, this is just the 1 plus 1 or the two-dimensional kinematic space that was working for the static situation. I erased that part of the board, but here I said static, yes? So this is for the static case. What about the four-dimensional object, which is not for the static case? So for the four-dimensional object, all I have to do is just take this thing and promote U and V rather than varying over a one-dimensional set of, rather than varying over a one-dimensional curve of endpoints, just allow it to vary over the whole set of x mu's, x lefts, and x rights. And this guy here will still have the properties that we want, namely, so this is now, if I allow mu and nu to vary over two coordinates, this object now defines a four-dimensional metric for me. And this four-dimensional metric for me, this that I wrote down here, will still have the property that if I take appropriately chosen two-dimensional slices of it, just like our static slice was a two-dimensional slice of it, then it will compute the length of a curve. In fact, the statement I just made is not exactly known to be true. It's something that I have been suggesting to Anael and Alberto and others to help me verify, but it appears to be true. But anyway, there's some very interesting interplay between two-dimensional slices of this four-dimensional space and lengths of the curve that remains to be explored. But we know that the statement I made here is explicitly true when we're on a static slice. Away from a static slice, it is probably true but unproven. Okay, but in fact, this metric though has many other interesting properties which are fun, so that's why I wrote it down. One is the questionable, probably true property that this equation will generalize. But what other fun properties does this metric have? So the other fun properties that this metric has is, I forgot to make, let me say this and then I'll go back to something. So the other fun properties that this metric has is the following. Suppose that I give you some general geometry which is asymptotically AdS free. But not exactly known to be AdS free. So that means that the length of any geodesic is going to give for me the some entanglement entropy. And from the knowledge of all of these things, I will write down a metric of this type. Okay? So you can ask, what properties of kinematic space metric guarantee that the metric that I started from is actually a solution of vacuum Einstein's equations? That this guy here solves vacuum Einstein's equations. That's a good question, yes? I can write down any metric that I want here. Most of those random metrics that I will write down will not solve Einstein's equations. Or they will solve They will quote unquote solve Einstein's equation with some arbitrary matter inside. But what about vacuum solutions? There are lots of vacuum solutions for the reason that I mentioned earlier, which is that in 2 dimensions, we're talking about AdS3 here. So in AdS3 CFT2, we have the enlarged Virasoro symmetry, which means that the vacuum has many, many descendants, and those many descendants correspond to, are considered to be different states in the theory. So they are the fact that they are descendants of the vacuum means that they are represented in the bulk as locally AdS3 geometries, but them being different states in the CFT means that we consider them to be different geometries. So they're locally AdS3, but globally different from AdS3. The question is, what selects, what property of this metric, which I constructed for an arbitrary geometry, would pick out or distinguish those which solve vacuum Einstein's equations from all others? So the way to do this is to say that I'm going to write my S entanglement as, okay, so let me write down the answer to this question. So on the previous, okay, it's a little more complicated on the circle, so I'm not going to, remember the formula that I erased from here before, which was V minus U over mu? This one was when my CFT lived on AdS cross time, on a sphere cross time, whereas this one was when my CFT lived on RD minus 1 plus 1, comma 1, yes? So please allow me to work in this case. So we're on the decompactified CFT, which is dual to Poincaré AdS. And I could make similar statements on the circle, but it's a little more complicated. So for the circle, my entanglement entropy, I'm just copying the formula that I have over here. S entanglement is of some interval that I have, which is a space-like interval. I wrote this over there as V minus U, but that was imagining that I have some particular slicing here. But in fact, I want to consider a completely general interval. I just want it to be space-like. So that completely general interval is again characterized by the 4 coordinates, which I judiciously erased just a moment ago. I'm going to call them ZR now, just for the purposes of this argument. ZR, ZR bar, and Z left bar. So unbarred means left moving, barred means right moving, L means the coordinate of the left endpoint, and R means the coordinate of the right endpoint. So in this language, the formula that I have over there is actually the logarithm of ZR minus Z left over some cutoff. And I had some cutoff here which was mu. Just to emphasize that I'm splitting this formula in 2, I'm going to call it mu to the 1/2 plus C over 6 log Z bar right minus Z bar left over mu to the 1/2. So notice that if I were on a spatial slice, then ZR would be ZR equal to ZR bar. Yes, if this interval was horizontal, Z left would be equal to Z left bar. And what I would have is 2 copies of the same thing, so I would just have C over 6 times the C over 3 times the logarithm of the difference in their locations, which is what I had over there. But in the more general case where I allow the endpoints to vary both in space and in time, this is the formula. So I'm going to call this guy S left, and I'll call this guy SR. It's a little confusing, the notation, because left doesn't mean related to the left endpoint. It means related to the left moving coordinate, which is unbarred. Whereas R means related to the separation in the right moving coordinate, which is Z bar. Yeah? So in fact, this formula here has 2 components, which is the S left plus SR. S entanglement is a sum of 2 things. So it will split. It will split into the piece which only depends on S left, multiplying the left moving coordinates, and a piece that only depends on S right, multiplying the right moving coordinates. And that's exactly what we saw before, because I have this product of two de sitters, yes? That's how the metric splits, yes? So the answer to this question is going to involve S left and S right separately, which is the reason why I go through it. So here is the answer to my question. What properties of the kinematic space metric will guarantee that the geometry I'm talking about solves vacuum Einstein's equations? So because the metric is given entirely in terms of entanglement entropies, I just have to give you an equation in terms of entanglement entropies. So let me just write down that equation for you. The equation is this one. D second S right D Z, this one is, let's make it Z left. Yes, so Z left depends on ZL and ZR. DZL DZR is equal to 1 over mu squared times C over 6. This mu squared is the same as this mu, okay? 1 over mu squared times C over 6 times E to the negative 12 over C times S left. That's the equation. So let me say a few words about it. So it's just some verbose comments about it. What is this equation? In words, this is vacuum Einstein's equations in kinematic space to nonlinear order. Yes? It's nonlinear because I have this exponential, so clearly there is no linear approximation going on here. This is an exact statement. This exact statement is a restatement of the vacuum Einstein's equations. If I'm away from the vacuum, any S entanglement is going to solve the theory or solve Einstein's equations with an appropriate stress tensor. So I would have to have the knowledge of the stress tensor, and then I would have to write some other more complicated equation. But I set the stress tensor to 0, and if I do that, the full nonlinear Einstein's equations will become these equations. So this is Einstein's equations in kinematic space, and let me just say that it's nonlinear. This is important because we will talk about linear equations tomorrow. But this is the nonlinear equations in kinematic space. The second statement is that I will have an identical equation for SR, because SL has to satisfy some property, SR also has to satisfy some property. So that's my second comment, that in fact I have two copies of the same equation. The third statement I want to make, and the third statement is probably the most surprising or exciting, is that we already know this equation from someplace. So the place where we know it, oh, I shouldn't have erased this, but okay, too late now. Or the reason why I can say that we know this is that this equation already has a name. It's the Liouville equation of motion. So what is Liouville theory? Liouville theory is this. If I take a metric, if I write down a two-dimensional metric in the form e to the 2 phi of u d times du dv, then you can ask the question, what equation would phi have to satisfy so that this metric has constant negative curvature? And this is a Euclidean metric now, for a moment. So I give you this metric in terms of one unspecified function. Any Euclidean metric in 2 dimensions can be written in this form. And I just ask, what condition does phi have to satisfy so that this metric has constant negative curvature? And the answer to this is d second phi du dv. Actually, let me use the same notation as I have over there. Z left, Z right. dz left, dz right. So the answer to this is that it has to equal to some quantity, which I will call rho, times e to the 2 phi. That's the answer to this question. And there is a field theory, which we call Liouville field theory, which solves exactly that problem. This shows up in many corners of theoretical physics. For example, when we compute, when we couple a two-dimensional conformal field theory to gravity, this will show up. Or, for example, when we compute, this is also what's called the uniformization problem. So if I have some string worldsheet which has some holes at the end where I insert operators, the easiest way to find what, or one way to find what that worldsheet would be, is to go to a conformal frame within the metric. The worldsheet theory has conformal symmetry. Exploit that conformal symmetry so that the worldsheet appears to have constant curvature. Well, this is going to solve that problem. It's going to find a way in which the metric will appear to have constant, the worldsheet will have constant curvature. And there are lots of other applications of Liouville theory to all kinds of physics. So anyway, this is the answer to that question. And notice that this equation has the same form as that equation. So evidently, Einstein's equations are actually Liouville equations, except that this description that I gave here for what the Liouville equations actually do doesn't really fit there. Because first of all, we're looking for the metric on kinematic space. So S left is going to control the metric on this part of kinematic space and S right on that kinematic space. But both of those parts are actually Lorentzian. So it's not the Euclidean, but a Lorentzian. Metric for which we're trying to uniformize, if you like. And the second thing is that this was one of the solutions, at least, was just the homogeneous two-dimensional de Sitter space. Yes, but de Sitter has positive curvature. So instead of talking about uniformizing Euclidean negative curvature metrics, in the case at hand, I want to find a metric for a Lorentzian positive curvature metric, which is this one. Yes. So it's different from the typical Liouville theory, and nevertheless, that's what it is. And one way I think to comment on why this equation had to show up is that we're looking for, the moment we posed this problem, we're looking for AdS, for spaces which were locally anti-de Sitter, which means that they were locally homogeneous. If they're locally homogeneous, their kinematic spaces should also be locally homogeneous. And if they're locally homogeneous, they should essentially be like de Sitter space locally, and then only different global properties. And evidently, this is the formula that picks out these locally de Sitter but globally distinct geometries, which is what I commented on over there. So, if you didn't find this illuminating, it is actually kind of confusing. I agree with you. But it's a very interesting fact that was pointed out in a paper by Rob Myers and Jan de Boer and somebody else, and Michał Heller and Felix Hell last summer. And this fact still has to find a home in our general understanding of things. So I invite you to think about it. Okay, so this was my third remark about this formula, the fact about Liouville equations. And then I have another remark to make, which goes back actually to the formula I raised over here, which was that length is equal to the integral du dv d second s entanglement du dv, which was an integral over some band in kinematic space, and that computed the length of my curve. So this formula here, it's actually, when we're talking about just pure anti-de Sitter space, so if we're in pure AdS, this thing is equal to dl d theta over sine squared L, okay? So in that special case, this formula actually has very many, in fact infinitely many generalizations in yet another direction. And that generalization is the following. So we already said that this object is like the volume form in the space of geodesics. So let me write it in let me rewrite this formula in a cartoon form as length equals an integral d geodesics. Okay. Now, the fact that I needed geodesics here to compute length turns out to be an artifact of the fact that we are in d equals 2 dimensions. If we're in higher dimensions, then there exists a formula of the same type where instead of geodesics, I will just have areas. It just so happens that in d equals 2, area is one-dimensional, so it's also a length. So we're also talking about geodesics. But I don't just mean any areas, I mean areas that generalize geodesics, so they are homogeneous areas. Okay? So areas that have constant, identically vanishing extrinsic curvature tensor in every direction. Not just in the trace that selects minimal surfaces, but in every direction. So it's completely homogeneous. Okay, so I have a formula of this type. Now let me further say, instead of length over here, let me write area of an n-dimensional space. Okay, I didn't just have to talk about areas in 2 dimensions. Let me talk about which was length. Let me talk about a higher dimensional object. It also has some intrinsic volume, which we call area. And suppose that these areas over here are r-dimensional areas. So the areas of r-dimensional homogeneous objects. Well, if n plus r is equal to d, then this n-dimensional object and any one of these r-dimensional objects are just going to intersect at one point, right? Because it's a zero-dimensional, they have complementary codimensions. Yes. There's a very special case in d equals 2 where a curve can intersect another curve in actually 2 points. Yes. But if that's if a curve is closed. But if I had 2 open curves, they would also just intersect at one point. So the generic situation is that they will intersect at one point. But what if n plus r is greater than d? Then I have objects which have sort of too many dimensions, so they will not intersect at a point, but they will intersect over some locus which has itself some volume, yes? So let me insert here volume of the intersection of area r intersect area n. So what this thing stands for is just the volume of the intersection of the object, which is the integrand, the dummy variable here, and the area whose surface whose area I'm computing. Does anyone still understand this formula, or did I lose everybody? I'm in an arbitrary dimensional space. All I have to assume is that it's homogeneous. I'm in a homogeneous space of dimension d. Okay? This is the setup. And let me draw it. Let's say that my homogeneous space is 3-dimensional. Yes? I'm going on the left-hand side. I'm going to select any surface I want. I don't care which one. So, for example, it could be a 2-dimensional surface, which looks like this. Okay? It's some surface that I have here. Is everyone following the drawing? It's just some 2-dimensional surface through here. Then, on the right-hand side, I will take the set of all possible homogeneous spaces which have the internal dimension r. So, because I drew here a 2-dimensional surface in 3 dimensions. So, what is this drawing? This drawing is d equals 3 because I'm in a cube. I'm in 3 dimensions. I have represented here a 2-dimensional surface, so n is equal to 2. Is that okay? And now I have to perform an integral of this type. So let me take an integral over all homogeneous areas which have dimension r. Let me select also r equals 2. If r equals 1, I will just have geodesics, and I will be back to the formula that we already talked about, which is geodesics piercing some surface. So let's take the next non-trivial object, which is r equals 2. So I have to consider all the homogeneous two-dimensional surfaces. What are two-dimensional surfaces? They're just planes, yes? And a plane is homogeneous. So I'm going to take any one of these planes, and this plane is going to intersect my curve at some particular locus, which I guess is going to be something like this. Okay? This is my area sub r. That's one. The length of this thing is what I have in this volume term. Now I'm going to integrate it over all possible areas. So I'll take this area and rotate it and do whatever I want with it in every possible way and take an integral of that. Yes? The statement is that the right-hand side will equal the left-hand side. And this is a generalization of the formula that we had before, except that on the left-hand side, instead of this green surface, I just had length. And these guys here were also themselves lengths. Lengths in two dimensions, two lengths intersected at a point, which means that this volume thing was also always equal to 1, so I didn't have to worry about it. And I was in two ambient dimensions, not in a cube. But this is a generalization of that statement. Does that make sense? So this is a generalization of the previous statements we made. For any choice of D, N, and R. Yes?
Aren't you just grouping lines into planes here? Essentially, you're doing the original integral over lines in a particular way where you group them into areas, homogeneous areas, and then you sum planes, no?
I don't think so. And the reason why I don't think so is that different...
Because that volume form you have on the right just counts how many lines you have essentially in your plane.
Well, what it counts is how many points I have over here,
Which
and every point here would have so many lines that intersected. So, yeah, okay, if you like, sure, yes, sure. And actually, what Chrysamalis just said, in fact, fixes something here. So you might say, oh, what about this measure here? So this measure is going to contain some extra factors of spheres of appropriate dimensions. And this factor of the volume of spheres in appropriate dimensions is going to account for precisely the thing that Chrysamalis just said. So yes, there will be some choice of measure for which is the correct one, which will make what Chrysamalis said more evident. But the point is that we have a formula of this type, and what we talked about previously was just a very special case of this formula, where I had geodesics intersecting other curves in two dimensions, which was a spatial slice of AdS3. But what about other dimensions? And there is no answer to that question that I know of in physical terms. This is just a fact of life. It holds for any homogeneous space. In fact, it's a very powerful statement because it holds for any homogeneous space, regardless of dimension. We already have this here, any dimension works. But also regardless of curvature, positive or negative curvature works. And regardless of signature, so whether I have a Euclidean space or a Lorentzian space, or in fact a space with more time directions, a formula of this type will also work. And but we only have a physical interpretation for one of them, and that one of them was the formula that I wrote over here. So what about the higher dimensional cases? You can say in AdS CFT, the area of any minimal surface computes the entanglement entropy of something. This area of an entanglement entropy by this formula will be given by an integral over some space of geodesics. Each one of those geodesics corresponds to some two-point function. So you can say, is there a way of deriving in higher dimensional CFTs a formula of this type? That entanglement entropy counts how many two-point functions care about or intersect my minimal surface. That's really what entanglement entropy is. Intuitively speaking, it should be true because entanglement entropy quantifies how much correlation there is between the region and the outside region. And any such correlation is mediated by a two-point function, which is the geodesics we're talking about here. So the formula should sort of be true, but if it's really, it has the right ingredients to have a nice interpretation. But if so, is there a way of working directly in CFT and using AdS CFT machinery to actually reprove this formula? And I don't know how to do it. So this is a very interesting problem that you may or may not choose to think about. Okay, so this is everything I have to say about the entanglement entropy side of kinematic space. And tomorrow we'll talk about how to put operators on kinematic space and what follows from that. Okay, thank you.
You say this is a mathematical statement and there's no to hold for any homogeneous space.
Yeah, it's on, yeah, and only for homogeneous space.
Right, and that's what I'm going to ask. Is it known that it doesn't apply? There's no generalization of this? Or?
So it's all about this choice of measure. So if in some cases, if I know the geometry, then we know how to choose this measure so that it still works. But these cases are so for example, the two-dimensional case that I told you about is an example of this, because I said, instead of talking about this, let me replace this with d second as entanglement du dv. This choice of measure works for any geometry I have. So that's an example of how we know how to choose measure. And in higher dimensions, there are some theorems which say that if a manifold satisfies the following very complicated conditions, then there exists a measure. That doesn't mean that we know how to write it explicitly. But there are some theorems which tell us that a measure like that exists for some very special manifolds. But I'm not too excited about, these theorems are so complicated and they're all existence theorems. I don't think that there's any hope of using them in a CFT context. But in the case of the vacuum, we should be able to see that the vacuum actually knows about this formula, or the dual of the vacuum, which is pure AdS, knows about this formula. And so, but just how? Yeah, somehow conformal symmetry should be powerful enough for us to recover this formula, and I don't know how.
What about solutions to Einstein equations with matter fields?
Yeah, so in general it's a very complicated problem, and there's a throng of papers that talk about how to derive Einstein's equations from entanglement entropy, assuming something to second nonlinear order or something like that. So the people who have championed this approach are primarily Mark van Ramsden and his collaborators. So in complete generality, this is a very difficult problem. And there is one particular case when we know the full nonlinear equations as well in the presence of other fields, and that's in a higher spin theory when I have spin-free fields. And in the presence of spin-free fields, these Einstein's equations, these Liouville equations, become what's called a Toda system of equations, which is basically the generalization of Liouville to spin-free fields. Okay, so it was the next obvious thing that you could have expected if you're the type of person who studies these things. But that's still a very special case, and spin-free theory has even more symmetry than Virasoro. So this follows from Virasoro symmetry. The spin-free fields have even more symmetry, so these are still kinematic statements. But that's all we should expect to have. Only kinematic statements will be derivable using these techniques. But in full generality, all you can do is order by order, and the best technique that we have so far has taken us to second order. So.
But if you consider systems, integrable systems, like AdS 5 crosses 5, then you have non-trivial R fields, the Dillard and everything, but you have a lot of, you have an infinite amount of
yeah, this question sort of goes in the direction of your earlier Grassmannian question. So, I fantasize periodically about being able to make contact with this, and I don't know how to, but on the level of faith, I'm sure that it can be done. Probably by someone smarter than me. I don't know how to do it.
But surely you need a lot of symmetry in order to do it.
Yeah, the statement about the Grassmannian statements and all that for amplitudes for n equals 4 superior mills are statements that this is an entirely symmetry-driven theory. It's it is kind of like Liouville theory in the sense that all you have to know is the symmetry group, which in this case is Virasoro, and in that case is the full Yanyan symmetry, which includes superconformal and dual superconformal. So there's probably some statements of that type that I just don't know about.
Related to Leon's first question just now, do I understand or remember correctly that in general, when you turn on interactions in your bulk spacetime, you're finding that in the kinematic spacetime, your equations are no longer local?
Yeah. So everything which equations? The equations that I talked about today? Or the equations that I will talk about tomorrow?
Well, when you have some nonlinear system as an equation of motion for your field in your bulk state vector, because this is a particular case, not this is
Yeah, but that's actually a local theory, so that's kind of a miracle.
This is local, but in general, you're finding indications that get non-local.
Yeah, so I'm surprised that you asked this question now because I didn't really say anything that would indicate this yet. But the truth is that we don't know how to understand interacting equations in the bulk of AdS. And there are various approaches to how to think about it. One approach is to say, suppose that I take the interacting bulk operators as we know them from the HKLL prescription. Let me just take I'm going too far ahead now, but let me just finish that sentence. Just take the X-ray transform of that and promote it to be the kinematic field. Then, sort of by construction, it's going to be a representation of an interacting field. Will it satisfy local or non-local equations of motion in kinematic space? And it appears that they are non-local, but then you could say, can I make the equations in kinematic space local at the expense of non-locality in AdS? And that's like doing the HKLL description, but starting from imposing locality in kinematic space. And you can do that too. But we're still looking. So we haven't written up a paper about it, partly because what I just told you is not very intellectually satisfying. So we're looking for some nicer way of getting some meat out of this statement, and I don't know how to do it yet. But it's very much something that we're thinking about. Okay. And actually, I want to say that for people who are interested, I might want to add an extra meeting on Friday because it's clear that I have more things to say than I'll be able to say tomorrow. And that's if you want to. I mean, I don't want to impose, but if there is interest, then I'll be willing to do more on Friday.
Yeah, we have 4 places.
So thank you very much.